3 that we're looking at. So in example 3, we have two functions. First one, y is equal to log base 2 of x. That's my red function here. And the second one is the blue function, y is equal to 2 thirds times the quantity x minus 1. I've written those, sort of expressed those functions as picked a point on the function and just written it in terms of x coordinate and y coordinate, and then here x coordinate and y coordinate. And for a here, we want to find the integral where we're going to rotate this bounded area between these two, so this area tucked in here, we're going to rotate that around the x-axis. And when we do that, we're going to get when we do that, we're going to get a washer, and we're going to have an outside radius of that washer. The outside radius of that washer is defined here. And then the inside radius of the washer is defined there. And note that these are two different washers that I'm talking about in the infinite progression of washers from where x is equal to 1 all the way out to where x is equal to 4, which is this intersection point. So the integral that I'm looking for is going to look like this. Pi on the outside, we are integrating from 1 out to 4, and we're doing pi r squared to get the surface area of the outside washer, and we're pulling the middle out, so that outside radius is defined here, right? So we're going from log base 2 of x down to 0. So this is just simply going to be log base 2 of x, the quantity squared, minus the radius of the inside circle of the washer. And so this is going to be 2 thirds x minus 1, all of that squared. And then again, our washers are along the our washers are along the horizontal, since we're rotating around the x-axis. So each one of those washers is dx. Right? Now if we flip this and instead rotate around the y-axis, we have to change our orientation here. So let me erase this. We are no longer looking for those two. What we're looking for is the outer radius is going to be of my washer. When I rotate it around the y-axis, outer radius is going to be that. The inner radius will be this right here. All right. Outer radius now defined by the blue. The inner radius, oh, that's a little confusing. Let's make our inner radius down below. Do our inner radius this way. That way our outer radius is bigger than our inner radius, even though we're in two different places. We're talking about two different disks, or two different washers, if you will. Now to get this distance here, we need to go from that point to the y-axis. Well, that point is x, but our integral, let's actually start writing our integral. We know we have the pi. We're going now up the y-axis, so we're starting down at 0, and we're getting up to this point here, which has got a y value of 2. Oops, didn't work. Y value of 2. And we want to get this outer radius, which means that we're going to want to take this and rewrite it in terms of y. So we can sort of rewrite this one as here, and then if we take our function and y is equal to 2/3 x minus 1, and we solve that for x, we'll find that x is equal to, oops, not 2, x is equal to 3/2 y plus 1. So then the outer radius, which gets squared, will be 3/2 y plus 1, the quantity squared. And then we're going to subtract our inner radius. So we want to take this and rewrite it. So y, and then if we know that, we'll do this down here, small below. If we know that y is equal to log base 2 of x, well then that implies that 2 to the y is equal to x, which then means that if we're writing our coordinates using y's, the x coordinate is 2y. So now to finish the integral, the inner radius is going to be 2y minus 0, or 2y squared. And then at the tail end of our integral, it's dy, because we're integrating up the y-axis. And we're done with example 3.